purpose of this video is to go over different threats to external validity. The first one we're going to talk about, we've already talked about a little bit earlier in the semester, and that's the concept of ecological validity. Ecological validity, think of that in terms of environment. How well does the environment or the setting of the experiment align with the setting the researcher wishes to generalize about? If the definition of external validity is the extent to which the researcher can generalize to the real world, that means we want the setting of the experiment to also align very clearly with the real world as well. For instance, you wouldn't want to do penalty kicks or an experiment that included doing penalty kicks on in the indoor field house. You'd want to do them on grass because that's more aligned with how you do soccer. Other names for ecological validity are interaction of treatment and setting or reactive effects of experimental arrangements. Population validity deals with how well does the sample represent the population. Here, we want to know, do the characteristics of the subjects who participate in the study actually align with the target population you want to generalize back to? This would be more of a problem if you're doing non-random sampling, because perhaps the reason they are non-random would suggest they are not actually aligned with the population. Another name for this threat to external validity is called interaction of treatment and selection. Interaction of treatment in history. This threat deals with the problems of trying to generalize results about different periods of time, either in the past or future. For example, as studies get older, we're concerned with the question, if we repeated the study today, will we find the same results? This is why commonly in your papers I encourage you to cite predominantly articles published in the last 10 years, because things published 15, 20, 30 years ago with different science, different understanding of the world, different technology might not actually hold up today. So that would be a thought that over time we can't generalize to past or future results. Reactive or interactive effects of testing. Here what we have is that the pretest may actually make the participant aware of what the treatment is supposed to be doing. So whatever your manipulation is in the experiment, just by doing the pretest, they have an idea of what it is they're supposed to be learning or being able to do better. So the treatment would only be effective if a pretest were given, because they have an idea of what's going on. But could not be generalized beyond the experimental condition because in the real world we don't have pretests. So that would be a potential issue. One way to deal with this is to remove the pretest, but you lose some important data. We're going to talk about what's called a Solomon design a little bit later. That's the best way to avoid this threat. That'll be in the next lecture. And then interaction of selection bias and experimental treatment. Here, sometimes what we have is that when you're trying to access certain samples from your population, some people will say no for non-random reasons, some people will say no for random reasons. But if you're trying to approach 10 schools, 9 say no and the 10th says yes, and the treatment is effective in the 10th school, it's really hard to generalize back to the other 9 schools because 90% of the people you approached said no or were negative responders. So that potentially suggests that your treatment would not work in that situation. Selection bias is typically related to the concept that people who are more interested in your topic or your manipulation are going to be more willing to participate in your study than those who aren't. So perhaps those first 9 schools really would not have been attracted to the manipulation or the treatment you were offering. Then there's multiple treatment interference. This happens most commonly in repeated measures designs where people receive more than one treatment level or more than one manipulation. Maybe you have 2 experimental situations or you have an experimental and control. If a carryover effect is present, then that is an external validity problem because in the real world, again, we don't experience multiple situations. We're usually either getting the treatment, for instance, the supplement or the exercise program, or we're not. So an alternative would be to use an independent groups design as opposed to a within groups design. So there are plenty of ways to deal with external validity. You can't remove all issues, but what you can, some issues, when possible, you can do random selection. so randomization does improve external validity. Blinding and double blinding studies will help. Using a counterbalance design. In a counterbalance design, what we have is we randomize the situation, we do a pretest, then this group gets a treatment, the other group does not get the treatment, we observe, now we switch, this group gets the treatment, the top group does not get the treatment, so I'll just scratch that part out, and we observe one more time. So in that type of situation, we counterbalance by allowing both groups to get the treatment, but at different times. So at both or throughout the study, everyone gets the treatment, everyone gets the control, but some get the treatment before the control, some get the control before the treatment, and you can better tell whether or not the pretest affected the outcome. And then just be very careful with your operational definitions and adherence to protocol. If you clearly define your variables, if you use appropriate measures, if you maintain your protocol, strict adherence to your protocol, then it's going to help you increase your external validity, especially if your operational definitions really do link up with the real world. Experimental control or the internal and external validity of your study is influenced by a number of factors, things from the very beginning when you develop a theoretical framework. This is more for my psychology, physical or education pedagogy individuals than it is for my physiology individuals. But your empirical framework or your science for my physiology folks. When you figure out who your target sample or target population is going to be, the development of your design and the application of your research design, how you choose to control your independent variables, what measurements you pick to make sure they're reliable and valid, how you do your statistical analysis, finally interpreting your results. So everything up here we've really talked about to some point already. What we have not talked about is this last part, which is the statistical model, or really what we're calling statistical control. Statistical conclusion validity deals with the inappropriate use of statistics that could lead to invalid conclusions. When possible, if you're using a statistician who's not involved in your study, and this would not be common for a thesis or a dissertation, but you would want to use somebody who doesn't actually know what your intended hypothesis is so that they can hopefully come to an unbiased result. But statistics are one of those things that while it seems black and white, it's very easy to play with the numbers to get what you want them to be. So it's making sure that you do the statistics in a very methodological, systematic, and objective method so that the outcome aligns with the findings of your study. Other things that could potentially affect your study in the internal and external validity are statistical power. Low statistical power is the ability to reject a null hypothesis when it is false. When you have small sample sizes, which is common in theses, it's common in physiology studies, it's common in dissertations, or when you don't control a number of sources of variability, basically you have a very applied study, that usually lends itself to low statistical power. So when dealing with that, you're going to be very more likely to commit type 2 error, where the chances that you're going to accept the null hypothesis when in fact the null hypothesis is false. The way that we deal with that is through randomization and increasing sample size. Violations of the assumption of statistical tests. We talked about this in the stats lecture or stats sections. People do parametric tests when they should be doing non-parametric. They don't see all these things. You really do have to make sure you follow the requirements, otherwise the outcome is really not going to make a whole lot of sense. You will get numbers. SPSS will provide you with numbers, but they won't actually have any true meaning behind them. Then there's error rate. With certain analysis, the researcher may have to perform a large number of statistical tests. Every single time you run an additional statistic, that means if you run 2 correlations and then you decide to run a third and a fourth and a fifth, what you're doing is you're reapplying your alpha, or you're reapplying your error rate. Because remember, alpha from the beginning is just the amount of allowable error. Well, if you do multiple tests, it means you're allowing more error into your study. So if you're doing multiple tests and you're not necessarily doing them accurately, usually there are other statistics. Instead of doing 4 t-tests, you can do 1 ANOVA to replace multiple t-tests. If you're instead of doing multiple ANOVAs, there's a statistic called a MANOVA that I teach in doc stats that can replace multiple ANOVAs. So there are other options that become more appropriate statistics and can increase statistical conclusion validity. And then finally, reliability and variance. Findings are threatened when extraneous factors increase the variability in the data. Essentially, if you don't control the extraneous factors or extraneous variables in your study, there's going to be your outcomes are going to be your participants are going to perform in a more variable way. As a result, your conclusions are not really going to make as much sense. Examples for what can increase the variance in a study could be unreliable measures, lack of consistency increases variability, protocols not being adhered to, influences of the environment, that would be a history confound, or other nuisance or confound variables. These factors, unless addressed by the researcher, are going to affect error variance and then probably increase the chance that you commit type 2 error. The higher error variance, the less the chance of achieving statistical significance. So again, this goes back to you have to adhere to your protocol, you have to try to control as many variables as possible. Alright, that would be the end of this lecture.